In this section, we're going to find the volume of a solid of revolution. So I showed you one example off camera. There's plenty of examples that you can see in your book of some things that have shapes that are solids of revolution. A rotor, a funnel, a pill, a bottle, a piston. So all these can be thought of as having been obtained by rotating something around an axis and sweeping out that volume. So we're going to try and find the volume of these kinds of figures. So let me go over to here and home view, slideshow. There we go, from current slide. So what's going to happen is we're going to take this curve and rotate it around the y-axis. Now for this first section here of this, let's just look at what happens in the bottom. You're going to start out by making a little partition. You're going to create some slices through our region. Now when we rotate that around the y-axis, that region is going to sweep out a volume. Now you see it up here. We want to pay attention to what's going on down here. When we rotate that region around the y-axis, it sweeps out a figure. What's this figure look like to you? Yeah, it looks like a circle with a little thickness, right? So we'll call it a disc, or let's see, at least for me, hockey season started last Sunday, so we'll call it a hockey puck, all right? So that's what we're going to be working with, is trying to find the volume of that one hockey puck, and then we're going to add up the volume of all such hockey pucks. Just like in the last section, we found the area of one slice, and then we added up and found the area of all such slices. So some of the work we did in the last section was really kind of like a setup for some of the stuff we're going to do in this section. So we'll start with problem number 2. So our function in this particular case is y equals 4 minus x squared. And we're going to rotate this around, let's see, the x-axis. So we're going to rotate this curve around the x-axis like this. And when we do that, that's going to sweep out a volume. Now, for this particular problem, and in general in this section, you're going to take a slice perpendicular to your axis of rotation. So in this case, perpendicular to the axis of rotation means you're taking a dx slice. Now let's think what's going to happen to that dx slice as you rotate it. Well, I just showed you a little video of what happens, and that what's happening is it's going to sweep out a volume. So let me do a little bit better job than that. So apply some Photoshop here. Beautiful. All right. When that sweeps it around, we're going to try and find the volume of that disc. So disc, or one hockey puck. So what's the volume of a disc? Really, it's a short cylinder. That's what it is. And how do you find the volume of a cylinder? Well, it's going to be the height times the area of the base. So volume is going to be the area times the thickness of our puck. Can anyone give me either one of these things? Well done. Pi r squared is going to be the area of this circle here, right? So pi r squared times the thickness. What do you suppose the thickness is here? Dx. Yay. Dx. So the only thing we don't know yet is what's the radius. what's that radial distance? So it's important that we get this thing right. And I'm going to do some things that, again, are a little bit of a setup for stuff we're going to do later on. So that radial distance is going to be the top minus the bottom. So the R, the radius, is top minus bottom. So it's going to be, if you wanted to, you could call this y1 and y2. y1 is this function, y2 is this one. But top minus bottom is 4 minus x squared minus 0. So that's our radius. It's 4 minus x squared. Let's put that in here to complete our calculation, or to complete our expression. Are you okay with the radius here? So we're rotating around the x-axis. So this distance is going to be your radius. Pi times 4 minus x squared squared dx. That's the volume of one of our pucks, of one disc. Are we okay with where I got that volume? So far, so good? Thank you. All right. Now, I need to add up all such possible volumes that I can get by slicing through this region. So we can do that with integration. So it's going to be what to what? Where should my limits of integration be? 0 to 2, 4 minus x squared, squared again, dx. And that pi, let me tuck that out in front, like that. I really hope that no one in this class squares this out as 16 minus x to the fourth. Bad, 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 bad. All right, you have to FOIL that out. No shortcuts. I mean, I guess there are some shortcuts, etc. Now, you know what? I've done a lot of these by just saying, you know, let's just kind of skip to the happy ending. Let's actually do this one out. So let me take that function and put it here. So pi times the integral from 0 to 2 of 4 minus x squared squared again. If you're really stuck doing this by hand, you got to square that out. My trick in squaring these out is to square the end terms, so that'd be a 16 here and an x to the fourth here. And then I borrow this 2, because you're going to get twice the middle term. 2 times this times this. So it's going to be a minus 8x squared in between there. If you can't do it that way, then just multiply it by itself and FOIL it out and collect like terms. The integral isn't too bad. So when I integrate that, I'm going to get pi times 16x minus 8x cubed over 3 plus x to the fifth over 5 between 0 and 2. 16 times 2 is 32. That's going to be 64 over 3 plus 32 over 5 minus 0. Typically speaking, I'm happiest if you wrap that up in a nice, neat fraction. If you include pi in all your calculations, you're not going to get that nice, neat fraction. We'll just throw pi in at the end. 32 minus 64 divided by 3 plus 32 divided by 5 gives me some number. Hit the math key and answer the fraction. And there we go. We got a nice, neat expression. 256 over 15 times pi. So 256 pi over 15. How's that first one? Okay on that first one? Yay? All right, thumbs up. Good deal. Let's see. Anything on this that you'd like me to go over a little bit more before I move on to the next one? No? So I entered all these numbers, and then once I got my answer, you hit the math key and then press enter twice, and it'll turn your answer into a fraction. Now, if I put pi in all this, so suppose I had all this up here, and then I had times pi, it can no longer be written as a fraction. If you hit the math key and answer the fraction, it's just going to give you back what you started with, because pi is an irrational number. You won't be able to write that as a fraction. So that's why I did it without the pi part. Is there a question? No? Okay. Say again? I hope so. You got me nervous here. Let's check. No, not that one. All right. We got any sound here? All right, laugh a little bit. There we go. All right, we're doing good. Thank you. Yeah, it is recording. So, thank you. Let's take a look at, let's see, problem number 4. Problem number 4. Yeah, all right. I know I'm skipping around a little bit. But I want to be friendly about this, so we'll do it. Problem number 4 next. So the function in problem number 4 is y equals the square root of 9 minus x squared. We're going to wrap that again around the x-axis. So this is your axis of rotation. This curve fits nice and flush against that axis. So we'll draw a little slice here. For the disk method, you're always going to take your slice perpendicular to your axis of rotation. That's something we'll actually practice a little bit later. Just trying to make sure that we understand which one's which. What's the thickness of this slice? dx. Yeah, good. Not a trick question there. It's dx thickness. Let's see about finding the volume of that one disk. So, problem number 4. Volume of one disk. Well, volume as before is going to be pi r squared times the thickness. So there's a couple things I'll need to know. I've already got the thickness, that's dx. I need to figure out what the radius is. And the radius is the distance from your axis of rotation to that curve. So again, I need to figure out what the top minus the bottom is going to be. So the top function is going to be the square root of 9 minus x squared. What's the bottom function? 0. So pi times square root of 9 minus x squared minus 0, 0 dx. Now this one's pretty nice because you get some good simplification here. What simplification do we get? Yeah, the square root cancels itself out. So it's pi times 9 minus x squared dx. Nice. Now that's the volume of one disk. But Brandon, I need the volume of all such possible disks. So I need to add up all those possible disks that I can get from different slices. How could I do that?
By limits of integration.
All right, and what should my limits of integration be?
0 to 3.
Perfect. Thank you. Nice. If you do that all out, what you'll end up with is 18 pi. And yeah, I am skipping the grunt work calculation again, sorry. I'm hoping that that's not a hard one to skip. By the way, does anyone recognize what that figure would look like if you rotate it around? Yeah, it'd be a hemisphere. It'd be half of a sphere, right? So if you rotate it around, and if you actually checked it with the formula for the volume of a sphere is 4/3 pi r cubed. The radius in this case is 3. For a hemisphere, we'd have half that volume, so 2 pi r cubed. 2/3 times pi times 3 cubed. One of the 3's would cancel here. You're left with 9 times 2 is 18. 18 pi. So it works. Right, the whole sphere would be 36 pi. Right. Okay. It was actually Archimedes that first came up with this formula, and he did that 2,000 years before Newton invented calculus. It was amazing. Archimedes, Newton, and Gauss are at the pinnacle of mathematical achievement. If you list mathematicians by their achievements during their lifetimes, going all the way back to antiquity, Archimedes is right up there with Newton and Gauss. So definitely some heavy hitters, and he came up with this formula. So bravo. He was really using methods of calculus before calculus was invented. Okay, let's keep going on our handout. Problem number 6. Problem number 6 is going to throw us a little bit of a curve. So we've got this shaded region here, and part of that is the curve y equals 2. Part of it is the curve y equals 4 minus x squared over 4. Now where are we going to rotate that? Around the x-axis? Yeah, around the x-axis again. So, getting dizzy going around the x-axis here today. It's all right. We'll mix it up soon enough. Now, for rotating around the x-axis, in which direction do I have to take my slice? dx or dy? dx. It still has to be perpendicular to that axis of rotation. But if you notice, there's something a little bit funny about this one. Can you put your finger on it? It's not fully shaded. That's true. What's it going to mean when I rotate this around the axis? Am I going to get there's going to be a hole in that. So you're not going to get a disc anymore. You're going to get something called a washer. And let's look back at that little video thing that I had here just a minute ago. Right here. No, I don't want to save it. Just show me current slide. If you watch the top part of this, you'll see that once you partition this up and grab a slice that's not touching the y-axis, when it rotates around the y-axis, you get a disc, or you get a washer. You got that hole in the middle. So we're going to have to work with that and see what that does to our calculations. Okay, let's escape out of here, back to here. All right, so this is problem number 6. So what's going to go on here is we're going to get a washer. And we're going to want to find the volume of that washer. So there's 2 different radiuses we're going to need to work with. I'll call the inner one R1, and the outer one R2. As far as finding the volume is concerned, it's not going to be rocket science. What we'll do is we'll find the volume of this outer disk and subtract the volume of the inner one. So that's going to be pi R2 squared minus pi R1 squared. And that's all going to get multiplied by our thickness, which in this case is going to be a dx. Now, to clean this up a little bit more, I'll factor out the pi. So it's going to be pi times R2 squared minus R1 squared dx. And that's going to be the volume of one washer. Let's see if we can't figure out R1 and R2 for this particular problem. Now notice R2 is the longer of these. It goes to the outside of the figure. So you start at your axis of rotation and you move to the outside of that figure. So let's extend this down a little bit. Should I label this R1 or R2? It's going to be your R2. And this little piece is going to be R1. So let's come up with some expressions for both of those. Those expressions are going to have to be in terms of dx, because that's our thickness here. So R2, top minus bottom, is going to be 4 minus x squared over 4. That's your top. Minus the bottom. What's at the bottom? 0. Just the x-axis. R1 is going to be a little bit friendlier. For R1, we're working with a different function. This one right here. What expression should I put in for top minus bottom for R1? 2 minus 0. Exactly. So your outer radius and your inner radius give you a top minus bottom. Both of these things simplify. And now we can plug those in and find the expression that represents the volume of one washer. The volume of one washer is going to be pi times 4 minus x to the second over 4 squared minus 2 squared times dx. And that's the volume of one washer. Danny? So where do you want to subtract? It's a good question. So if I did this minus this and then squared it, it wouldn't work because it's not following your order of operations. Your order of operations say you have to do the exponents first. So it's a good question, but I have to square this before I do my subtraction. All right, it's a good observation though. Anything else on this one at this point? Yeah?
This is similar, but could you just do top minus bottom? Bother with zeros?
Well, the only reason I'm bothering with the zeros, yeah, you don't have to do, you don't really have to put the minus 0, but soon enough we're going to have an axis of rotation that's going to be something different than 0. So I just want you to get into that habit of knowing top minus bottom or right minus left. So, eventually we will use it. Yeah? Good question. our limits of integration are going to be in the x direction, right? So they're going to be this way. Now, it looks like they're from -3 to 3, doesn't it? That's what it roughly looks like, but it's not.
0 to 3 and times 2.
No, it doesn't go all the way to the x-axis. Your limits of integration have to be along the x direction, because this slice can be taken anywhere, right? As long as it's in this region. So what we have to do is we have to figure out, well, where does this curve meet this one? We've done that before today, even though the video before it got screwed up. Does anyone remember what we did to find where these 2 points intersected? Yeah, set them equal to each other. So what that's going to mean for us is we're going to set this function, 4 minus x squared over 4 equal to 2, and then solve for x. So let's solve. Now for myself, I guess there's a couple different ways you can do it. What looks convenient to you? Tell you what, most of you don't really like fractions. So let's do this. Let's get rid of the fractions. I'll multiply everything by 4. This is not to the 4th power, it's just multiplying everything by 4. I'll get 16 minus x squared equals 8. Okay. Let's move this to the other side. 16 minus 8 equals x squared. Plus or minus the square root of 8 is x. So it's a little deceiving. It kind of looks like it's from -3 to 3, but it's close. It's plus or minus 2 square roots of 2, which is about 2.8 something, 2.82 maybe. Those are your true limits of integration. So I think we've got everything we need here. We've got our integrand. We've got our limits of integration. Let's set that up. So it's going to be the integral from -2 root 2 to 2 root 2. Pi I'll put out in front. 4 minus x squared over 4 squared minus 4 dx. Yeah, nice observation. This is an even function. If you notice, this graph is symmetric with respect to the y-axis. So this is an even function. So if you're trying to make this a little bit easier, you could double the integral and go from 0 to 2 square roots of 2. Or if you're entering this in your calculator, it might be easier just to enter it as the square root of 8. Your calculator doesn't care if you've prettied that up a little bit. 4 minus x squared over 4 squared minus 4 dx. And that's just a beast of a calculation to square it out, simplify it, etc. So unless somebody really wants to see it, we can jump to the happy ending. You know, I'm not going to make your grunt work too terribly bad. You know, the bottom line in this one, I think it turned out to be 448 square roots of 2 over 15 times pi. Yeah, it's just not a whole lot of fun. Hopefully, you should be able to do it. This is Calc 2. I mean, it's really not much more than a polynomial. It's just squaring it out. It's just to play around with all the square roots and get it all nice and neat and tidy. It just isn't that fun. One of the options that I would have here would be to say set it up and come up with a numerical approximation. You know? So can you do that on your calculator numerically? Can you type that into your calculator? Okay. Then if you did, you should get something close to 132.69. That's an option. But I hope I've made it clear that I do expect you to be able to use the FN int key of your graphing calculator.
So where's the 2 pi go when you do that? When you type that stuff in, where does the 2 pi?
Well, I would do this and then multiply it by 2 pi. Yeah. So, and if you wanted to look at some of the gory details, they're right here. So you just square this out, simplify that, you get something like this, and then you get all these. And then what I did is I ignored the square root of 2, worked with these to get a fraction, and then put in the square root of 2 and pi. So anyways, that was my approach. Nice. Anything else to wrap up on problem number 6 here? Yeah, please.
R2 will be the thickness and the radius minus the R1.
So R2 characters in Star Wars, right? Where'd I go here? Let me get back here. So R2 is that outer radius. So it's going to be this minus the inner radius, or that distance to this function which represents the axis of rotation. And R1 is similar. Distance from here to the axis of rotation. It's always top minus bottom, or soon enough, we have to do right minus left. Yeah, basically 1 is empty space. The nice thing about R1, this inner radius, is that it's not changing. It's basically just a cylinder, right? It's all you're getting from this inner space. It's the outer space that's a little bit more interesting. All right, good questions. Let's try some more. Let's do a couple versions of problem number 12. So on the bottom of your handout, you should have a couple graphs for problem number 12. And let's see. In the first one, they ask you to rotate around the y-axis. Like this. If you rotate around the y-axis, in what direction do I have to take my slice? Horizontal. Good. Remember your slice is going to be perpendicular to your axis of rotation. So perpendicular is going to mean this. You're going to take a dy slice. Now looking at your dy slice, is this going to end up being a washer or a disc? Got to vote for a disc? Washer, disc, washer, disc. Well, you're going to get a disc if your whole figure is completely flush with the axis of rotation. So here was a disc. But in problem number 6 and in this one, there's a gap between your figure and the axis of rotation. So that's what gives you that hole that's going to make it a washer. So this one's going to be a washer, rotating around this point here. What's the thickness or height of my slice? dy. That dy is important. I always write it down here, but the reason I write it is because that's telling you that your integrand has to be in terms of y. So that's going to be a little bit more challenging then. Our functions here, this is just the graph of x equals 2. I think that's y equals 2x squared if I'm not mistaken. Yeah, y equals 2x squared. So that's this curve right here. Y equals 2x squared. I'm going to have two different radii. this one, and this one. So my outer radius is going to be called R2. The inner radius is going to be called R1. And I'm going to try and find the volume of one washer. Now that volume overall is going to be pi times R2 squared minus R1 squared times the thickness. The thickness in this case is going to be dy. So the real work of this is going to be to try and find expressions for R2 and R1. Let's start with R2. That's going to actually be the easier of the ones in this case, right? Because it's going to be the right minus the left. So if I give that point general coordinates would be 2 and some height y. Over here, this point has coordinates of 0 and y. Right minus left is going to be 2 minus 0. Just 2. That makes sense. This is a constant thickness, constant radius of 2. But here's where I'm going to have to work. The coordinates at this point, I'm just going to make them general. Call them x and y. I can still find this distance. It's still right minus left. X minus 0. But because my thickness is a dy thickness, it's not enough to have this as an x. I need to solve for that in terms of y. So how are we going to do that? Well, y equals 2x squared is that function. If I divide both sides by 2 and then take the square root, I get my expression for x. So what I'm going to put here is that expression. Square root of y over 2. So it's a little bit of bonus work that we haven't had to do for some of these other problems. We had to actually solve for that term. I think I'm ready to put all this stuff in and find the volume of one washer. So, are we okay with our calculations of R2 and R1? Finding those two is the big thing here. Yeah, please. All right, so when I'm finding that distance, it's right minus left. When we're subtracting in the x direction, you subtract the x coordinates. So the coordinates here are 2 and 0. And then likewise here, it's x and 0. So that's where I'm subtracting those. If this was a problem and I was taking a vertical slice, then I'd be subtracting top minus bottom. Then I'd be subtracting, the y coordinates. Okay? So we'll... Yeah, you're always still going to go right to left. So even if this was on the left side of the y-axis, you'd still be subtracting right minus left. Correct. So let's put all that in. Find the volume of one washer. That's going to be pi times 2 squared. And this will work out nice. Square root of y over 2 squared times the thickness, which is dy. So basically pi times 4 minus y over 2 dy. A lot of work to come up with a simple expression, but that's the expression we need to help find the volume here. Last but not least, I need to figure out my limits of integration. So I'm going to integrate that. Let's take the pi out in front. 4 minus y over 2 dy. The thing to keep in mind is that this dy slice can be taken anywhere here. So what's the lower limit of integration? 0. Along the y-axis, it's 0. And all the way up to the top, 8. Now, if you're looking at that going, well, gee, without a good graph, how am I going to know that's 8? That's pretty fair question. And here's a nice answer. You've got y equals 2x squared. Put in the 2 here. 2 squared is 4 times 2 is 8. So you're going to integrate from 2 to 8. Or I mean 0 to 8, I should say. So, Photoshop, running out. There we go. So that point would be 2 and 0. So we're going to integrate from 0 to 8. Okay. It's up to you. Do we need to integrate that or happy ending? Happy ending. Yay. Good answer. 16 pi. All right. I'm hoping that one's not too bad. Okay. This is 7.2. Yeah. So, tell you what. Let's take a break here. I have 2 more problems that I'll finish up with. So I'll see you in 10 minutes.